Hello everyone, Victor is here, and in this video I want to go over some SN1 and E1 practice problems. So here's the list of the problems that I want to talk about today. So what I suggest you do, take some paper and copy these problems one on each piece of paper, or at least leave some space between those problems so you can fill in your work. Then, once we start talking about each of those problems, pause the video, work through the problem, or pause the video and work through all of the problems right now, and then look through the answers and through how I work through those problems. Okay, the question number one here is this one. And when I'm looking at my compound and my conditions, the first couple of things that I'm noticing right away that I have here a polar product solvent, which means that SN1 or E1 reactions are going to be possible. Next, I'm going to look at the position of my leaving group. The leaving group in this case is my bromine atom over here, and that is a tertiary position, which means that the leaving group dissociation is going to be quite easy. We are going to form a tertiary carbocation. So step number one is going to be my leaving group dissociation, giving me a carbocation intermediate looking like this. This is already a tertiary carbocation, so this one is a tertiary position, so I am not going to be expecting any carbocation rearrangements or anything of that sort, because in this particular case it's impossible to make my molecule any more stable than what it is right now. So the next step is going to be our nucleophilic attack. The nucleophile in this case is going to be just our methanol, so I'm going to rewrite my methanol molecule CH3OH here, and the electron pairs that I have on my oxygen going to be my source of the electron density for this nucleophilic attack. So I'm going to say that the oxygen is attacking my carbocation like this. And as a result of my nucleophilic attack on my carbocation here, I'm going to get this protonated intermediate. Now, this protonated intermediate is not particularly stable because we have a positive charge on the molecule, so we would really like to get rid of that positive charge. And the only way how we can do so is by getting rid of our proton of the oxygen. So I'm gonna say that I have another equivalent of my CH3OH here floating around, and typically these reactions are done in an excess of the solvent, so having an excess of our solvent floating around is not an issue here. So CH3OH is going to come by and pull that proton off, giving me a neutral molecule as a result. Alternatively, you can see that sometimes we also can show that the Br minus, which was our leaving group from the very beginning, and it is floating somewhere around, we can use that to pull our proton off. So sometimes we use that just for the sake of the stoichiometry of the reaction to show that the HBr is a coproduct and to show through the mechanism how exactly that product is formed. And so my final product will look something like this. In this case, we do not have any chiral carbons or anything of that sort, so we do not have to worry about the stereochemistry, so that's just one product that we are going to get here, and that's it. So the next reaction here is an alcohol with sulfuric acid and some heat. The delta sign over here is a common abbreviation for the heat, so whenever you see a reaction with this delta sign, it means that we have a reaction at elevated temperature. So since we have high temperature, acidic conditions, and alcohol as a starting material, that is probably a recipe for the elimination reaction, for the dehydration reaction, so most likely we're looking at the E1 reaction here. And the very first step in this reaction is going to be protonation of my OH, because OH by itself is not a good leaving group in neutral or acidic conditions like that, so I first have to protonate it, and then it becomes my leaving group. So now, when I do have my leaving group, the H2O over here is my leaving group, I can have my leaving group dissociation, which is going to give me a new carbocation, looking like this. And here is something important about this carbocation. I noticed that this is a secondary carbocation which is right next to a quaternary position, which means that we are extremely likely to have a carbocationic rearrangement before we can do anything else in our molecule. So I'm going to do that. I'm going to take this methyl group over here, and I'm going to move that with all of its electrons onto the position where the carbocation currently is. And as a result of this carbocation rearrangement, I'm going to get a tertiary carbocation. But it's not just a tertiary carbocation. This carbocation also has resonance stabilization. So I can show another resonance contributor here from our double bond, where we take the electrons from the double bond and move it over here. So that is going to give me the second contributor looking like this. So I have a tertiary and I have a primary resonance contributors for this carbocation, for this allylic carbocation over here. And because I now have two electrophilic positions in my molecule, I have an electrophilic or electron deficient position over here, and I have another electrophilic or electron deficient position over there, it means that my nucleophile, if I had one, could attack either of those positions. It also means that we need to consider both of those positions when we are dealing with the elimination reaction. In this particular case, we do not really have any good nucleophile because sulfuric acid is a very strong acid, and whenever we work in extremely acidic conditions like that, the nucleophilic attack is extremely unlikely. However, since we also have an elevated temperature, we know that we are most likely looking at the elimination reaction. So for the elimination reaction, I need to look at the beta hydrogens next to my carbocation. So hydrogens on carbons adjacent to my carbocation. And if I look at the top molecule, I have hydrogen over here. Let's call it hydrogen A. I also have hydrogen over here. I'll call it hydrogen B. And I also have a hydrogen over here, and I'll call it hydrogen C. So potentially we could get a product from all of those hydrogens. Also, if I look at my bottom molecule, then for that one, while the only place where I have adjacent hydrogen is going to be over here, let's call that a hydrogen D. So if I were to take the conjugate base of my sulfuric acid acting as a base, so if I have HSO4 minus over here, and let's say I'm going to pull off my hydrogen A like that, then what that's going to give me is an elimination product looking like this, and I'll keep it color-coded so it's easier to see what's going on there. If I do the same thing for hydrogen B, then what I'm going to end up with is a molecule that looks like this. If I do the same thing for hydrogen C, well, that one is going to look a little bit funny because I have a double bond carbon, then another double bond, and then the rest of my molecule. And finally, if I do the same thing for hydrogen D for my last resonance contributor, it's again going to give me this, then carbon, the double bond that I already have, and then the rest of my molecule like that. The next thing, we know that we got to look at the stability of our double bonds and figure out which of the double bonds that we form is the most stable, and that's going to be our major product per Zaitsev rule. When I look at my molecules with the cumulated diene over here, where the two double bonds are right next to each other, those are not the most stable type of alkenes, and if you haven't covered alkenes in your course yet, you will learn later on that those are definitely not among the most stable alkenes, so we're pretty much not going to be considering those. If I look at my orange and my purple molecules, I have two alkenes over here and over there in each of those molecules. Those are what we would call conjugated alkenes. They are next to each other and they are very stable. However, if I look at the orange molecule now, let's call the top bond here bond A. The bond A only has one non-hydrogen connection. The bond B over here has two non-hydrogen connections. If I do the same analysis for my purple molecule, I have bond A and bond B. Bond A again has only one non-hydrogen connection, but the bond B is 1, 2, 3, 4, it's connected to 4 non-hydrogen substituents. So overall, the bond B in the purple molecule is significantly more stable than the bond B in the orange one, and therefore, purple molecule overall is going to be the most stable alkene out of all possible ones, making that into the major final product. There we go. So as you can see, sometimes in elimination products, you are going to end up with a ton of different products, and you have to very carefully analyze everything that you know about the molecule in order to figure out which one is actually going to be a major product. Here is the next question. And here, again, I have a good polar protic solvent, which can potentially play a role of my nucleophile in the molecule. And if I pay attention to where my leaving group is located, and the leaving group is this bromine over here, that bromine is sitting on the tertiary carbon, which means that that is a perfect position for us to eliminate that group and make a carbocation, because the tertiary carbocation is relatively stable. So once I have my leaving group dissociation, I'm going to end up with the carbocation looking like this. And here is something interesting. I have two competing nucleophiles in this molecule. I have the isopropanol molecule that I have as my solvent, and I actually have the OH, which is the part of the molecule itself. So that oxygen has a couple of electron pairs on it as well, so that can as well be a nucleophile. And here is an important thing to remember. Intramolecular reactions, so reactions within the molecule itself, they typically happen much faster than intermolecular reactions. So here we can, in fact, use the OH inside of our molecule for the nucleophilic attack like that, giving me a 1, 2, 3, 4, 5, 6. It gives me a 6-membered ring. So the easiest way to draw a 6-membered ring for the molecule like that, for the reaction like that, would be to start with a 6-membered ring containing the oxygen. So I will draw my oxygen, and then I have a 6-membered ring for the rest of the molecule. Next, I will renumber my ring, going 1, 2, 3, 4, 5, and 6. So with my curved arrow over here, I'm showing that I've made a bond between oxygen and carbon number 6. So oxygen never broke a bond with hydrogen, so I still have hydrogen sitting on my oxygen here. Because of that, my oxygen is now going to be positively charged. Then, going through the rest of my molecule, I also have a couple of methyl groups on carbon number 6, so I have this methyl group and this methyl group, so I have to add those to my molecule over here, and that gives me my intermediate. Finally, this intermediate, like in the previous example, is a protonated intermediate, so it's not particularly stable, which means that I'll have to deprotonate it in order to make the final product. And as a conjugate base, or as a base in general, that I'm going to use here to pull the proton off, I'm just going to be using my solvent, or, like in the previous example as well, I can use my Br-. Statistically speaking, the alcohol is going to be a more likely base, simply because we have physically more of it and it's floating around, but for the stoichiometry's sake, I can use my Br- as well. And so my final product will look like this, a 6-membered ring with a couple of metal groups sitting next to my oxygen, that is the carbon number 6 right now. So when it comes to reactions like that, always make sure you double check for any possible intramolecular reactions, because questions like that are fairly common on exams, and there is a very high chance that your instructor is going to throw something like that at you. So be always very careful with that. And as a rule of thumb, remember that if we can make a 5 or a 6-membered ring in the course of a reaction, we are going to make that ring, because 5 and 6-membered rings are very thermodynamically stable. 6-membered ring is the best out of all of them, but 5-membered rings are also possible, and occasionally 7-membered rings too. 3 and 4-membered rings are significantly less stable, and they are significantly more rare guests in our reactions, although 3-membered rings sometimes do form in SN2 reactions, but a 4-membered ring is essentially a huge no-no, so pretty much never make a 4-membered ring unless you know for sure that that's a specific reaction that does make a 4-membered ring, or you are instructed to come up with a mechanism that includes a 4-membered ring or something of that sort. Alright, here is the next question. And in this question, we have a compound, which is a secondary iodide. This is a secondary position. This is also a benzylic position, which means that the leaving group dissociation here is going to be extremely easy due to the resonance stabilization of the resulting carbocation. We also have acetic acid here as our solvent/reagent, so that is a polar product solvent, which is going to help us make our carbocation by pulling the leaving group off, and we've got high temperature here. So again, it is likely to be an elimination reaction because elimination reactions are favored at elevated temperatures. So step number 1 here is going to be the leaving group dissociation, giving me a carbocation that looks like that. I am not going to show all the resonance structures here, but I will just remind you that there is a ton of resonance structures that we can draw here, and as extra practice I do challenge you and encourage you to draw all of those resonance structures and see for yourself how many you get. Hint, you are going to get 4 resonance structures total. Anyways, going back to my question, since we have a high temperature conditions, as I said, we are likely to have the elimination product as the major product on our reaction. So if I look at the position of my carbocation, the only place where I have hydrogens that I can potentially pull off are at this beta position over here. So I have a couple of hydrogens over here, and I only need one of those. Notice that there are no hydrogens on the left side because that carbon is already connected by 4 bonds, so there is no place for the hydrogen over there. So what I'm going to do here, there are 2 options that I can use for the conjugate base to pull off the proton and make my reaction go. I can either use the I- that I used as the leaving group that dissociated from my molecule as a leaving group to begin with, or I can use the acetic acid itself. Neither of those are particularly good bases, but as I've mentioned in my previous video, carbocations are so incredibly acidic that they don't really care. They will dump that proton onto anything that even has an electron pair, regardless of how good of a base that is. So here I can say it's either iodine or my carboxylic acid that's doing the deprotonation part, and we are going to end up with the final product looking like this. And notice that the double bond that we got in this case, the double bond over here, it does have the stereoisomerism. It can be either E or the Z isomer. Here is the next reaction. And in this reaction we have 2 potential leaving groups. I have a chlorine as a potential leaving group, and I have an iodine as a leaving group. However, the iodine is sitting on an sp2 hybridized atom. So, as my iodine is sitting on an sp2 hybridized atom, that's a trap. Iodine is not a leaving group in this case, so I am not going to even consider that. And although iodine is a better leaving group, because it is on the sp2 hybridized atom, it's pretty much non-existent to me. So the actual leaving group in this case, and the only viable leaving group, is going to be my chlorine. Then I have my polar product solvent, which means that the formation of the carbocation is going to be relatively easy because the solvent will help my leaving group dissociate. Also, this is the allylic position, so this is over here is a secondary allylic position, which means that the resulting carbocation is going to be resonance stabilized. So if I draw my leaving group dissociation step right like that, I'm going to end up with the following carbocation. And as I've mentioned, this carbocation is stabilized via the resonance, so I am going to show the other resonance contributor, which will look like this. So I have a secondary contributor and I have a primary contributor to my resonance stabilized carbocation, which means that now I again have 2 electrophilic positions, and since the reaction seems to be happening at room temperature, I don't have any indication of temperature here whatsoever, so I can assume that temperature is a room temperature after all. It means that the substitution reaction is probably going to be the major product here. So what I'm going to do, I'm going to say that my ethanol CH3CH2OH is going to perform the nucleophilic attack on either position. So we are going to have either this attack or we are going to have that attack over here. In the first case, I'm going to get an intermediate looking like that, and in the second case, my intermediate will look like this. So from this point on, the only thing that I have left is to get rid of my proton and get a neutral product. So in order to do that, I'm going to use another equivalent of my ethanol that I have floating around, and I will show that it will pull off my proton from here or from here like that, giving me the following two products. And one other thing that I am noticing here is that in my top molecule I do have a chiral carbon over here, which means that I'm going to get two possible stereoisomers. So I can redraw that as these two molecules, and these are going to be enantiomers. So as a result, in this reaction I'm going to get a pair of enantiomers, which my top two molecules, and another constitutional isomer or structural isomer, which is my bottom molecule over here. So my final products are these two guys and this one over here. And here is my last question for today, and in this reaction I again have a polar protic solvent, so I have protic conditions, I have heat, so likely I'm looking at the elimination reaction, and I have an amazing leaving group here in the form of the tosylate. And I'm going to remind you real quick that the tosylate here is that monstrosity, and since that molecule is very big and ugly, or that moiety in the molecule is big and ugly, we're going to typically abbreviate it as OTS, but it's still a good idea to know how that group actually looks like in real life. So, since in this reaction I have polar protic conditions, heat, wonderful leaving group, which is sitting on a secondary carbon over here, the first step is going to be my typical leaving group dissociation, giving me a resulting carbocation. Now, what I get here is a secondary carbocation, which is right next to a quaternary position. So again, like in one of my previous examples, there is an extremely high chance of the carbocation rearrangement here, so that's exactly what I'm going to do. I am going to take this methyl group over here, move it with all of its electrons onto the place where my carbocation currently is, giving me an awesome new tertiary carbocation. And since this tertiary carbocation is already as stable as it can humanly be, or should I say carbocationically be? I don't know. Anyways, since that carbocation is already as stable as it can be, we're not going to expect any carbocation rearrangements or anything of that sort. So from this point on, we're going to analyze where we have our beta protons, beta hydrogens, and what sort of elimination products we're going to get. So I have my hydrogen A, and if I were to pull that one off, I'm going to end up with a product looking like this. I have hydrogen B, and if I were to pull that one off, I would end up with a product looking like that. And also I have couple of hydrogens C over here, and if I were to pull one of those guys off, I would end up with the final product looking like this, and since this double bond can have the easy stereoisomerism, I can do this or that. Now, doing the analysis of my double bonds, I can see that in the first case, in the orange case for the hydrogen A, for that one, I have a double bond with 1, 2, 3, 4 substituents on it. For the purple one, for hydrogen B, I have a double bond with 1, 2 substituents on it, and for the green one, for the hydrogen C, I have a double bond with 1, 2, 3, and the same thing for the other stereoisomer, 3 substituents as well. And since we're looking for the most stable double bond possible, which is typically the most substituted double bond, it's going to be the top one where we have 4 different substituents, so that is going to be our major product in this reaction. Hope you guys found this little walkthrough helpful, and if you did find it helpful, give it a like, subscribe, ring the bell so you don't miss any of my future tutorials, and I'll see you in the next video.